Let's not.
Let's not. Okay, I guess we're live now. I don't know, I'll put this on TARDIS now as well on Gita. Hey guys, you can start asking questions.
Oh, I need to log in together actually. I haven't done that yet.
We're live. And we are still at 0 viewers.
If you build it, they will come.
Can you send me the Twitter, whatever link?
The Twitter? Oh, Gitter.
Gitter, whatever.
Gitter dot. So it's gitter.im. No, dot im/TARDIS sn. TARDIS. Do you see that in the chat?
I can see it.
I can see, but I cannot log in.
No, it's you just need your GitHub account.
Yeah, the GitHub account is on Linux.
Oh.
And I'm now in Windows.
Oh, I see. No, but you can. You can
not
see,
in mind.
You should be able to see the
I
question.
see it, but I cannot
Yeah.
describe. I think it's probably better if I don't write something.
Why? But you can interact with the audience, with the non-existent audience, by talking. I mean, no. Last time we were more popular.
No, we have
It's still
1 minute.
Yeah, it's still 1 minute to go until
Okay,
like
1 minute is over. Okay, nobody's coming. See you.
the masses until the masses. No, I mean, no. I'm sure like we'll have 150 viewers in no time. One viewer. We have one view at least. And I think I also did the what do you guys look for in a proposal? It's difficult to say. I think it's different for the different projects. I think so. I wonder if Stuart wants to take this as he is taking real students. Well, I mean, not that you're not real students, but I mean he is taking students in real life. That he said face to face, and I think maybe you want to say what do you look for in a student, Stuart?
So what do we look for in a proposal or a student? I guess we look for enthusiasm. Someone who is taking the time to think about what they are planning to do, and
Oh, wait a second. I mean, no. I'm just asking. Not air. I hope that can you CSP FRCKS? Just making sure.
hopefully.
Hello. I mean. Okay, very good. I mean, we have at least one person
Yes.
here answering on
Yeah.
Hangout Air. I think he wasn't on Hangout Air. I hope.
Okay.
Well, I mean, no. I think it's okay. So you can see us, PFRCKS. Okay. Well, I presume you can see us. So the question was, what do we look for in a proposal? And Stuart was fielding that question.
Yeah. So I mean, it's difficult to say exactly, but I think I mean, you're looking for someone who has taken the time to think about it, and is sort of bringing sort of ideas to the table. I mean, it doesn't. We don't expect everyone to have the sort of astronomy information or the background or whatever like that, but someone that's just taken the time to think about what it is we're trying to achieve. And enthusiasm, I think, is a big part of it. I mean, we're enthusiastic about this project. We do it because we're interested and because we want to do it, and we want other people who will join in on that. So, yeah.
I think what I want to add to this is I think we're looking for also initiative. If someone if someone has it goes in and sees what problems there are with the code. I mean, we all understand that you're not experts in supernova radio transfer, but I mean, if you ask specific questions rather than saying oh, how does that work, but saying what does this mean? I mean, that sort of leads us directly to the next question, and I hope what are we looking for in a good proposal is sort of answered. We can come back to that later. So what is the
I-
sublab escape?
Can I just interject a little bit?
Sure, go ahead.
So since I know a little bit about how to get selected for Google Summer of Code, having been selected like 5 times now, I think the most important thing is specificity. The more specific you are about what you're going to do, the more impressive it is, I think. Like including which files you're going to change and in what order are you going to do things. It's hard for it to be realistic, but if it is, it's very, very impressive.
Yeah, I think seeing some of the applications, like if you can specifically say at what week we're going to do what, and rather than saying I'm going to build I'm going to build just a web interface, and basically there's no more information than that. But if saying I'm going to use this framework, I'm going to use that, or like with the GUI, I'm going to do this, and here's some picture of like how I would do this, or how it would look later. Like this helps us sort of understanding things.
It shows that you understand the problem and what the people in the project need from you.
Yeah. So I think we can go to the next question. What is the Sobolev escape probability? Which I think I'll let Stuart take.
Yeah, okay. So Sobolev escape probability. So Sobolev theory is a piece of physics which describes how photons are interacting with matter. And in the particular case of an explosion, so where the material is flying outwards, one of the things it predicts is if you create a photon inside a parcel of gas, it gives you the probability that that photon can actually get out to be seen. So microscopic physics would tell you what's the probability of creating photons, but our question is not just about whether they're created, it's whether they can actually get out from the parcel of gas where they were made to the observer. And so in Sobolev theory, this is what the escape probability is. So it's a physical quantity you can calculate, which says what's the probability that having made a photon, it actually gets out. And so if we're trying to predict what we see, that's a key part of the story.
So does that answer your question, Gautam? You need to type to us because we can't. Well. Okay. I don't know. We can actually have a look if there's any questions on this Q&A thing. I don't know if that works. No. Hey everyone, Amol Agrawal. Okay. Well, I mean, we're here to answer questions. I think that's the best thing for now. Like, we talked to quite a few of you about your proposals, and for some few people, we've now looked at some of the proposals, but we're sort of going through the list for now. And so, as we also have other things to do, day jobs, it's not as fast as it would be. So Gautam asked follow-up questions. So there's one beta for each shell.
There is one beta for each shell for each line transition. So the escape probability depends. So you're right, it varies from shell to shell. So it depends on the local conditions where the photons could be created, but it also depends which process is creating the photon. So when we have different atomic transitions, so the transitions between energy levels of atoms, it depends. Why do we have a large? Yes, so the large set of betas for each shell, there's one beta for every transition between two atomic states. And so that means, yeah, there's an array of them, which is, but it's kind of an array. You can more or less think of it as an array as a function of wavelengths of the light. And what those wavelengths are the wavelengths where the photons are able to interact with atoms. And so it depends on which shell you're in, but also which wavelength of the light you're looking at. That's why there's lots of them.
Okay, does this answer your question, Gautam? Gautam 1168. I hope so. Okay. Well, I mean, there's not much else to say than answering questions. I don't know if there's anything else we should talk about from a GSoC point of view. I think for now, we're looking through applications and things like this. But make sure that you have everything in Google Mirage by the 27th of March. So it's nice that if you write us on Gitter or something like this, but officially you need to have an application in the system and connected to us. Otherwise, your application is not valid. Put your first draft up there already. I think as far as I know, you can change it later. Okay.
Yeah, there does seem to be a long delay.
For us, yeah, it seems a very large delay. So, is that true for? Well, we can just do that on. No, I guess so. You could go to the events page and ask questions there. Maybe there's some questions there. You can go to the events page and you can ask questions there. Maybe this is faster. I don't realize like how long it takes until for us it seems like a minute until something comes back. Yeah. Maybe that's faster. I guess not. So here's the next question.
Okay, so then if I want to visualize the beta, then it would be okay to do it separately for each line. Yes, probably. I mean, it would be useful to be able to visualize how, for example, beta varies for a given line. So if you pick one line and then you could like visualize how beta changes from cell to cell. It can also be, that's actually, you're right, that's probably the more useful thing. You could also visualize in a given cell how the beta changes sort of with wavelength, but I don't think that's so useful. So I think what you said is probably right. You would pick one line and then visualize as a function of different shells what it looks like.
Okay. Well, I mean, so maybe you want to take PFRCKS's question first. So in case if a person is not selected for TARDIS and GSoC, can they still contribute unofficially? So TARDIS, to make this perfectly clear, is BSD licensed open source. Like anyone who is interested and who is willing to put in time is more than welcome to help us build this. I mean, everyone is welcome to contribute, to have a look, to be interested. I hope that answers the question, and then we can go back to Endarm's question, which is why you built TARDIS. Well, I mean, making spectra. So supernova spectra are observed. So basically, there's multiple modes of observing, and the main two modes are either you take a giant DSLR and strap it behind a telescope, and then you make an image, and you can put filters in front of this, like a blue filter or a red filter or a green filter, and sort of image the supernova or the object that you're looking for. in different filters. Or instead of putting a giant DSLR, well, you still use a giant DSLR, but between your DSLR and the telescope, you put a little prism. So you break up the light into its components. And that's what's called a spectrum. And so why we build TARDIS is to basically analyze a spectrum. So one way to find out something in physics is to go in and make a model, try to make a computer model where you can control what your input parameters are, and then see if that matches your observations. And that's why we built TARDIS, to eventually change these model parameters for TARDIS, and then see if that matches up an actual model in if that matches up with an actual model in with an actual observations. What makes TARDIS unique? I think many codes in astronomy, many maybe in other sciences are open source. I don't know, Michi, do you want to comment on this? No.
No, I was throwing something to Uli because he is trying to bring the law.
I see.
I can maybe say a little bit to this.
Go ahead.
So, is there other software that does the same? What makes TARDIS unique? I mean, yes. There are other codes that people use to do similar type of analysis, but so perhaps the most unique feature of TARDIS compared to any of its competitors that I'm aware of is that it is a fundamental part of what we're trying to do, that we're making the code publicly available and usable by everyone. And that means that it can actually be used by basically the whole astronomy community who are interested in supernovae. So that's one of the unique features of TARDIS. To my knowledge, there's no other code that can be used to analyze the spectra that Wolfgang was just talking about in a way that is open to everyone. I'm involved in other projects. I'm an example of someone else who does have another piece of software that it doesn't quite do the same in detail, but it is basically a code for studying supernovae spectra. But that's an example of a much bigger code. It's a code that runs on supercomputers rather than on sort of a laptop or whatever, and it's not practical for the whole community to use codes like that to do this kind of thing. So the idea of TARDIS is we're trying to make something available that is useful to everyone, and that everyone can really see how the code works. The science community can interrogate it and see what it's doing, and they can make judgments about how to improve it, what's good and what's not good about it. So I do think that's one of the main selling points.
Good. I hope that answers your question, Endarms. Yeah. Just to reiterate, this is for your benefit, the GSoC students' benefit. Like, if you're interested in anything, if you have questions, specific technical questions, astronomy questions, general questions, that's the time for us to easily ask the team and sort of get it answered. We have a new question. I got him. Since there are many data sets that have so much, since there are many data sets that have so much information like the beta that cannot be shown clearly in one single plot, should I think it would be useful to try to make animated or interactive plots? Since Matplotlib is still not very good at these, should I look at d3.js as an alternative? I mean, d3.js needs a JavaScript, so it needs to be run on JavaScript. I think Matplotlib, is very good at interactive plots. Like, you can have sliders and things like this. I think it's more than enough for what we are thinking or trying to do. I feel like it should be fine to do most of the things that we want to do. I mean, there's lots of information in the code, and one could also say, is it really important to visualize every single one of them? So the JBlues, okay. So one thing that we always suggest to people is run things in IPython. So by the way, for everyone who will apply or is interested in applying, I suggest you become comfortable with IPython. It's a very powerful interactive interpreter, and so you can play around with the model. Like, you can run the model and then see and then plot for yourself, because we cannot foresee every single, like the betas, every single need for some researcher to plot something. So we will provide with a GUI that I guess Gautam is talking about. We will provide some basic basic plots that is very useful sort of to do first sort of look through. But if you want to have some more detailed stuff, we suggest running these things, running TARDIS interactively, and then plotting the things yourself. So the next question is, what is JBlue? And I'll let, I don't know if anyone who wants to take that one.
I can do that unless someone else wants to. So JBlue, so this is similar, a little bit related. So it's another part of Sobolev theory. It's another quantity that comes into this question to do with how, when you were describing how photons interact with matter in this exploding, expanding cloud, it's specifically what it is. It's the ingredient that tells you how intense the radiation is. And again, it's as a function of wavelength. So a bit like the beta Sobolev you spoke about before, it's a quantity that has a value for every wavelength, essentially, for where all the transitions are in every zone. So it matches up. So essentially, everywhere that there's a beta Sobolev, that same transition, that same zone will have a value for this JBlue quantity as well. And it's a measure of how intense the radiation field is, and that's relevant because it affects how the atoms interact with the radiation.
I hope that explained it, Gautam. So the next question was, why was Dalek built? How does TARDIS plan to use Dalek in the future? And I can maybe begin, and I don't know if Vitalis wants to sort of add then something to this. So currently, how Dalek works is you give one specific set of parameters. You give whatever luminosity you want. You give one luminosity, you give one inner boundary, and you specify, the precise abundance for 10 different elements like oxygen, silicon, iron, and so on and so forth. And then you run TARDIS, and it will give you a spectrum back. And this is very good. If you want to have a realization of what one spectrum looks like. But one thing that we want to do with TARDIS is actually fit a spectrum. So basically, we have some sort of optimization algorithm, and we can, I guess that's where TARDIS is the expert in. We have some optimization algorithm that can sort of tweak all these parameters and then do an evaluation and see how it looks, and then change the parameters to try to make this better, to try to make this more or closer to an observed spectrum. And so that's where we need to, for the optimizers that we are using, we have, 20,000 function evaluations. So each evaluation of TARDIS takes roughly 5 minutes. So if you do this one after the other, this will take a long time. And that's why Dalek that's why sort of the Dalek API is built. Basically, you can attach an optimizer, or you can tell it to do a grid of like, I don't know, 10 by 10 by 10, and so then you can tell it to Dalek, and Dalek can connect to a supercomputer and sort of run as many cores as you give it at once. And so that's the main part of Dalek. So I think, I don't know if there's anything you want to add, Vitatus.
Well, as for the future, I think we want to expand Dalek to do what? Wait.
I think for the future, for Dalek, we want to make sure that it has a nice interface. Like currently, this is sort of a very much working code in the sense that, like, you know, Vitatus was working on an optimization problem. I had some idea how to build Dalek. I was very much in favor of using IPython Parallel, which is a very nice interface to doing running code on many processes, and sort of we put this together to fit our needs, but it was never done in a nice way. So in the end, what we would have as part of Google Summer of Code, and I should mention as Google Summer of Code, this will be very much a team effort. Like all the things that people are working on will interlink, and we hope that people will talk to each other about, like, what they're doing and like how this interacts with stuff that other people are doing. And so we hope that Dalek will evolve into something that is well documented.
So we also want to expand Dalek to use more shells and to interpolate the abundances between shells, right?
Yeah, I think we sort of want to make sure that basically Dalek is able to handle the full different inputs that are currently given in the YAML file.
So that we can specify spectra in a time series, as in spectra how the supernova evolves, and maybe we're hoping that will help the optimization process that will give the optimization process more information to go by.
Yeah. So I mean, that's also sort of doing things.
Another thing that would be very nice is to, as Wolfgang said, ideally I would like to run some kind of, I don't know, maybe a script that I could just specify the spectra to, and I didn't need to bother logging into the supercomputer, installing the newest Dalek, then worrying how to name the output files, how to collect them. So in general, an easier, more convenient way to run optimization on supercomputers to encourage experimentation with different algorithms and making development easier.
Yeah, I think that's sort of the main part of the summer project, making it easier, making it nicer, and then, like, helping make it compatible with what our scientific goals are. So I think that's what's going on. So there was one question. So what is JBlue? Dalek build. The next one was similar to the Narayanaditya 95's question. What about Cassis? Well, Cassis. Okay, so Cassis, or we'll have to think of a name because Cassis already exists. Is the idea of using atomic data sets from multiple sources. So TARDIS needs atomic data sets. So Stuart mentioned this before because Stuart talked about the different states of atoms and exactly where these different energy levels for the atom are. Like, this is done by atomic physicists that sort of put together the information into giant, text tables or into giant databases. And multiple groups measure or calculate the same levels, And there's also, so it's the levels of the atom that are interesting, and it is basically the transitions between these levels that are also interesting for TARDIS. And as multiple groups calculate this in slightly, or measure this in slightly different ways, we have sometimes multiple values for like one level. And so for us to be able to compare how different this is, or what the difference is in the actual output, we would like to have a database. There's other things about this database. We can compare two different, just looking at the numbers and see, like, how different are the values, and why are they different. So we can learn a lot more about this. I don't know if Stuart wants to add anything to that.
No, I think that, I mean, there's a lot one could say about the atomic physics, but I think basically that is correct, yeah.
Yeah. Okay, the next thing is, what will the timeline of the plasma project be like? Can you give some details? Well, I mean, I think for the plasma project, it's a moderate project. It's not an easy project. You should have a look, like, to know what the old version, the plasma_array, how it calculated things, and then see, like, what the new version is. I mean, there again, as we specified before, the more specific your questions are, the easier we can answer them. The idea for the plasma project is sort of have a modular way, so calculating the plasma state of the for supernovae, you sort of have different modules that do different things. First, you want to know how many atoms there are, because so you basically have a density given and you have a volume given, and that allows you to calculate how many grams there are, and then you can see, like, how much does one atom weigh, and you can then calculate how many how many atoms of this type there are, and then you want to know which state they are in. So all of these calculations sort of plug into each other, and then it goes down the line, and more complex calculations follow. And so Mihi and I have thought of a way to sort of easily plug this together. And currently we have implemented some of the stuff that was in the old, very inflexible plasma array.py, and ported it to this new structure. And in the new structure, we hope that, not all of the functionality from the old structure is there, and so I think, like, one of the things that would be useful is to go and look what's missing there. I don't know if you want to add anything to this, Michi, in general about the plasma, or if...
No, I think you have mentioned everything close to the plasma. The big point is still the data transfer from the Python plasma array, alias new plasma structure,
yeah,
to the C part from the Monte Carlo code.
Yeah, this will be
one big deal.
This is something that Mihi is specifically working on. This is, like, less about the GSoC project. The GSoC project mostly focuses on actually making sure. So we currently have a set of working plasma calculations, and making sure that the new framework gives the same answer as the old framework. So I hope that answers the Lupac 0577. So the next question is on Gotham again. You told me that you were making a new model for Run TARDIS. What are you aiming to change? The current model has one field MDL GUI, which is assigned the value none. What is its intended use? I think for now its intended use, it's supposedly none, and will stay none, because I think I never used it. So this was one of these things where I thought it would be useful for the model to have a GUI associated, but I unfortunately never took it out, and that's bad. Like, that's why we advocating this testing and also restructuring of TARDIS project, where we sort of look through things and say what's needed, what's not needed anymore. So currently the model sort of has a lot of things stores a lot of things, including the plasma state. It also includes how many iterations a model has done. It includes things about the Monte Carlo process. And so these are all sort of separate things that sort of are linked into this model. And in the end, like, quite a few of the things that are displayed in the GUI, like temperature and dilution factor, we do want to keep in the new model. but there's quite a few things like I don't know how many iterations it has done. We don't want to put in the model, but we want to have it in a different class, similar to Plasma. So these are sort of separate, separate things. I hope that answers maybe some of the question. Gotham 1168. Okay. Good. Was there anything on the Q&A thing? Nope. Okay. Well, I guess, I mean, if there's no significant questions, I think we can. Okay. We could. There's another. The original idea was to call it Karsus, which is a library planet in Doctor Who, because it's sort of an atomic library. There has been lots of thought going into naming of, maybe more so than actually writing the code. But no, I mean, yeah, there's multiple ways, but we can discuss this. Yeah, I don't know, once we start. So I think, like, if there's no significantly more questions, we can stop in, I don't know, in 10 minutes. Then it's 1:45. Does that? That's a little bit slow, I guess. We have one more. We have.
Wolfgang, you're muted.
Well done there. Thank you very much for that, Stuart. So yes, I think.
Not that I'm complaining. It's quite nice.
Shut up. Anyways, this is the lovely banter we have going on in this team. So yes, I think it would be useful for whatever thing runs the simulations afterwards to have some sort of callback function where you can say, well, I mean, once you're done, once you're done with one iteration, call that callback function, and it could update the GUI, or it could update a web app, or it could update something else. And I think, yeah, in the end, that's a sensible thing to do. So Aditya95, who will mentor the web app project. One of the people who will mentor the web app project is currently not here. So it's Andreas Weiss and Roland Thomas are both people that will mentor the web app project. I'm interested in the web app project, and as we discussed the other day, we are not sure what framework to use. Actually, I think Michi has also expressed some interest in helping out with or mentoring the web app project, because he has, I think, worked with both Tornado as well as Django, and maybe he wants to comment on things. There was a discussion so maybe Michi there was a discussion about Tornado versus Django, and so it would be useful maybe to hear from you, because you've worked with both.
I was muted, sorry.
All right.
So Tornado, I know Django, I know Flask, but Tornado is new for me.
So I think Flask is also. I mean, no, it is Django versus a smaller framework.
Okay.
So I guess the question is, I suggest Tornado, or I suggested Tornado because IPython uses that, and so when we install IPython, which is lots of people do, already the requirement is fulfilled. They don't need to install something else. But it's, I think, general Django versus smaller things. So.
So for me, both are fine. I think only that smaller framework like maybe Tornado, I don't know, or Flask is a little bit handier to use than Django. So I don't think the project will be getting so big that we need Django with all its features.
Yeah, I mean, is there any specific downside you can think about, Michi, that Django has, where we need to set up a whole lot of things so we can actually get it working, or is it similar setup? It's just many features that we won't use.
I think there's a database framework already included in Django, so we don't need this. So we need only a small text file or database as backend. So this is one big part of the code which is completely unused. Then there are a lot of security features already built in Django. This is not bad, but I also think this is not necessary for our case.
I think it mandates a database. Like you need to have some sort of database to even start using it. Maybe I'm wrong. I think.
Yeah, so in case of emergency, I think you can run it with SQLite. So there's a file and it's built in. Yeah, probably a whole database only to maintain the web GUI is a little bit too big for the project. I think very thin coded Flask GUI or maybe Tornado GUI, or maybe also some CGI scripts.
Yeah,
will be fine.
So I mean, the main, I think like Django is fine. I mean, in the end, like in the end, like we'll not downgrade people on what web framework they use. I mean, if you say I use Tornado because of X, Y, Z, then it shows us that you have thought about this. If you say I use Django because at X, Y, Z, I mean, it would be great if you could say I use Tornado because Django and Flask, these are just examples, don't have these features. Or if you say I use Django because Tornado and Flask don't have what I need. So I think what we're looking for in applications, and I think that's the main question, is like you specifying why you use a web app rather than saying this is a web app that I've been using for a year now. I've learned, or like I've learned at school or something like this, and that's why I want to use it. So because for us in the end, someone from Google Summer of Code might just leave and then say, well, I mean, thank you very much, and is gone. And then it relies on the team members to sort of maintain this. And if we can use something that some of the team members like Flask or Tornado already use and are familiar with, then this is better than introducing something new. But maybe there's a good reason. I mean, to say, well, I mean, we can easily build this with Django, and it's very simple. And if you want to change something, you just need to change this file, and then this is okay as well. I think we just want to make sure that it's not because not specifically you, Narayan, but anyone who's applying is familiar with the web framework and then says, I'm going to use that one. But because people have looked, we want the application to reflect that people have looked at multiple web frameworks and say, this is the best for the project, and that's why we're using it. Anyways, I hope it basically answers your question, Narayan. The next... Okay, good. Is it possible to look at intermediate values as TARDIS reiterates? Yes, got him without the 1168. It is. Well, you can just run it for less iterations. So you can set the number of iterations. Often we set it to 30 because we think it sort of converges after 30 iterations, but you can just set it to less. It's not as easy. I think there was a functionality in there, I don't know if it still is, where you could save to HDF5 files for each individual step. That makes it, that's what we want to do. But in the end, if you have a graphical user interface, I mean, this was something that Stuart just said before. He said hey, what about is we could just let it run for one iteration, then it stops, and if you want to see the next iteration, you click go again, and then it does the next iteration, because this would be great, because it would help us a lot to sort of figure out for certain physics how they work, or what is the problem, or where we could make it better. Go ahead.
I think if I'm understanding this right, I think I mean, you mean you want to look at the various values of the variables during each iteration of TARDIS, right?
Yeah. That doesn't mean
So,
each photon. Just means each iteration.
yeah. So I think it's possible to make a C function that would register a callback. So a callback would be written in Python and could call Python code, and that it would get called once, I don't know, once every iteration or.
I think you don't need a callback in C, since the iteration are already done from Python. So the Monte Carlo part is called for each iteration from the simulate.py. There's the flag setting the number of packages and the plasma parameter and the computed parts.
I mean, what Michi is saying is right. I mean, no, it's about the iteration. We're mostly talking about not the iteration over the multiple packets, but we're talking about the general iteration that sort of converges temperature and temperature and dilution factor.
I thought this was moved to C, wasn't it?
No. This is just after. I mean, in the end, we could do both, but I think for now, what we want to do is we want to do the Python. There's a Python loop. We want to use a Python loop to do that. So. But I mean, in the end, yes, I mean, we would like to have for the Python loop this, and I mean, if we get to this, it would be great fun to also have some some hooks in C, but I think that's sort of a secondary feature. The other thing that Stuart, I'm just like telling what Stuart wanted before. The other thing that Stuart was talking about is like it would be great if you could just update these values. You could say, well, I mean, the temperature that you got here. I don't think it should be 12,000. Or what happens if I now change it from 12,000 degrees to 6,000 degrees for the next iteration? So, have not only an input, but also have an general input, but also allow these input parameters to change while running this. But this is like more of an advanced thing. For now, the graphical user interface is good or is okay, but it's not great. And I think there's many things that we can do before we do these advanced things. Okay, the next question is, if we vary only a single parameter while keeping the rest the same, can we predict how the output spectrum would vary in response? I think I'll let maybe Stuart and Vitalis take this.
I can say something about that. So the answer is somewhere between yes and no. It does, as you say, depend on which parameter you're talking about. And also it depends about how accurately you mean these things. So it's generally not too hard to predict the sense in which things will go. Will the spectrum get brighter? Will it get fainter? Things like that. But to be very quantitative and say it will change by 3% or 5% or something is usually very hard. And that's kind of why we need a code like this, because it is difficult to predict why, how the input parameter, essentially it's a very nonlinear problem. So it's very difficult to predict. It's not chaotic, but it is very nonlinear. So you can predict. It's very difficult to predict if you put in, say you change the abundance of one element, exactly what the knock-on effect of that will be. And so that's kind of why we need a code like this. I don't know if Vital just wants to say more, or maybe not.
You muted Vitalis.
I accidentally closed Gitter. Which question was it?
About the extent to which, how hard it is to predict how changing a parameter affects what you see.
How hard is it to predict how? Well, I don't know.
So I mean,
if we could predict that, we wouldn't need optimization, would we?
Right. Yeah. So that's kind of what we're saying. That's a major reason for writing the code. The other thing I would say here is an interesting thing from the physicist's point of view is also that there are many parameter degeneracies or near degeneracies, and they're often very complicated ones. So in practice, That's one of the things that one gets out of a code like this, is understanding not just how if you change one parameter that affects what you see, but how changing parameters plays off against each other. And so particularly from the point of view of the optimization project, that's a very interesting part of it, is understanding the degeneracies between the various parameters. And that, as a physicist, as an astrophysicist, is a big part of the question, because you want to know, when you take data, the spectra that Wolfgang was talking about a while ago, when you take your observation and you want to make sense of it, it's not sufficient to just say, oh, here is one solution that can explain my data. You need to be sure whether your solution is unique and what information you really get. And so a code like this is part of understanding that.
Yeah, so I think the answer is that there's no easy way.
Just quickly interrupt. So Michi has to go, unfortunately, and I guess we'll see him again next week, and we'll see if we can do one more. And now, sorry, Vitalis.
See you. Bye.
Bye.
You were saying something. I just don't remember what.
No, I was just saying, yeah, there's no really an easy way. I wonder why is this person interested in, why did they ask this question? So were they expecting to use some sort of, I don't know, gradient-based algorithms, or?
I don't know. I guess it was just a simple thing to see, if you would have if you could vary a single parameter, how easy it is to predict what the output spectrum does. And I mean, as both Stuart and you have said, we need to use complex algorithms, because no, it's not that easy to predict this. And I mean, an algorithm maybe we can predict, well, one change, but maybe in some other. So the other parameters also affect this whole thing. Maybe this is one important thing. One parameter, if you change this, might have a different effect on the spectrum than if the other parameters are different. So I wonder, should we add more to this, or should we just go to the next question?
Yeah, well, but it's my understanding that people can, to some extent, predict. I mean, if they couldn't, they wouldn't be able to do the fitting manually.
Well, I mean, you could do it. I mean, even if you do it manually, you could just scan through the parameter space. Yes, I mean, you're right. You can, to some extent, predict, but it's not a simple mapping. It's a very complex thing. You take into account many things.
Yeah. So I think that's the point. So I mean, just to reiterate that, I mean, I think the thing is, it's not too hard to make a rough estimate, to qualitatively know that if I change this parameter, my spectrum will become bluer, or this feature will become stronger or weaker. So if you're doing it by hand, you can sort of push things in what you think is going to be the right direction, and you'll usually be right. But it's very difficult to be quantitative and say, I have to change this parameter by 10% rather than 15% to achieve a particular effect. Because, as I say, the response is just, it's non-linear, and there's lots of second-order consequences. Very often you change a parameter, and the main thing it does is make the spectrum bluer, but it turns out it has some knock-on effect where something else changes as well. And very often trying to fit things by hand, it's like one of these problems of trying to squeeze a sleeping bag back into its box, and you sort of push in one direction and it looks like it's going right, but then suddenly it pops out somewhere else. And that's sort of why doing this more systematically would be a lot better.
Yeah, I mean, I think that's sort of a good answer from all accounts. The next question was by Gautam again. You said that you wanted TARDIS to install and run with a double click. I can do something about running TARDIS GUI with a double click, but wouldn't the installing part have to come from a person who packages TARDIS? Also, double click installs doesn't make sense on Linux, and on Windows you will have to distribute Python 2. Well, I mean, this was sort of more of a phrase of saying, basically you wouldn't have to, you would double click some sort of symbol. I mean, to just reiterate, as much as we would like to also make sure that things work well on as many people as possible, we do in science often exclude Windows because it does not have the right requirements for actually running scientific code. So what we do for TARDIS as well, we make sure that it runs on Linux and on Mac because both of them share a Unix background, but we don't have the resources to distribute to Windows. And yes, I mean, in the end, we'll make a GUI that sort of you can start and first from the command line, maybe then some sort of symbol. But I mean, for Mac at least, I know you can pack everything, the Python and everything, into one package called an app. And I've seen people make Python apps, but this is also down the line. There's so many things we want to do with the GUI first before we make this possible. And I hope that sort of answers it. Got him. And I guess we have another 5 minutes left, and I guess, yeah, I mean, now's the time to ask questions. Should we have a look at the Q&A section?
Do you have any specific list of atomic sources you want to include for atomic database project? Or research can compose many such sources. The major one that we would like to start from is, I think you've already looked at this one, is we sort of talked about it a bit before, is this Karut's line list. So that is a very widely used source in astronomy, and it's kind of in some sense the standard one. There's a scope to go beyond that, and in a medium or long term, it would be great to be as flexible as possible and actually be able to compare as many different sources as we have. But I think to start off with, we're primarily interested in the sort of standard Karut's list, and there's also something called the Chianti database that we've used before, which is very good for certain ions of certain elements. You've included 4 as of now. I mean, that sounds like a very good place to be starting. Can you type which 4 you have? I
don't know why, but I think there's some sort of delay and lag in there for whatever reason.
Yeah.
While we're waiting for PFRCKS question, I mean, Gotham, yeah, you can try to fit your own, but, well, I mean, no, I'll find one for you.
Okay, unlike Karut, we don't have as many elements. That's correct. So this is one of the reasons that we often use, or not always, but in several astronomy applications, the Karut's line lists are widely used because they do cover all the elements. So yeah, okay, so you've got Karut's, Chianti, top base, and this. Yeah, so those are 4 very important, very standard ones. Those are all good ones to be working with. The big difference with the Karut's calculations is that, so they are calculations, and for the most part they're theoretical calculations, and you can actually do those, or he has done those, for a great many of the elements. And so that's very valuable for us. most of the other databases, NIST and to an extent Chianti as well, are more focused on actually presenting well-verified experimental data. And so typically, if you take NIST and Karutz in a sense, I think are probably the two most extreme ones in your list there, in that the Karutz one is very extensive. It has extensive models for many elements, but many of the individual values in those databases are not perfectly accurate, whereas NIST is very focused on getting very accurate values for experimentally verified things. Yeah, so VALD, the Vienna Atomic Line Database, that is also quite widely used in astronomy. In part, I think it is itself uses some of the same data that comes from Karutz originally. I mean, those are also going to be good things to have in the end, but I think in the short term, my guess, in the short term, we'll have enough to do properly making sense of Karutz, comparing it to things like Chianti. Top base is a very important one because that's actually going to be our source of a different type of data from Karutz, so that's something called a bound-free opacity. And so connecting up Karutz and top base will be very useful. I think if you were to focus on those four that you talked about to start with, that would be a great start. Extending to something like VALD later, yeah, that would be good too. And as you say, there are many others out there. So I wouldn't say, I don't think it will be useful to try and make an exhaustive list of, because we can easily find 20 or 30, and I don't think that's sort of necessary, at least in the short term.
I think, what one should also mention, just using the Karutz, nothing else, but just the Karutz, I think is already is already something that we can spend a lot of time on getting right. And I don't know. I think that will have quite some effort within the 3 months' time to sort of make sure that we are able to parse all of this information, and we can then play around with it a little bit before we go further. I mean, it's great to have the idea of what to do next, but I also feel that we need to focus on the basics first, like building the database structure, thinking about the database structure. So I think this is probably a great idea. So there was a question about where to get an observed spectrum from, and Gautam, I'm going to throw you into the cold water, as they say in Germany. That means this will give you an overview. I suggest clicking on the SN 2011 FE data release, and you can have a look in there. I think there should be spectra in there. And it has also a nice movie where you can sort of see how the spectrum changes over sort of the different periods, and you can see how much brighter it gets. This is plotted in so-called magnitudes, which is in astronomical units, and you can see how the spectrum evolves. And I mean, our code can reproduce this 11FE spectrum reasonably well. But yeah, I mean, by all means, you can try to fit it, but it's very, very hard. And I mean, maybe it's a fun exercise for you. I mean, if you want to try. Okay, I guess it's 7:01. I think for now, I think that's fine, right? I think that's it for now from us. We'll see next week is the 26th, which is one day before the applications are due. So we'll have to see if we have time to sort of do another videocon. And yeah, I mean, we'll put this up there, and if you can come, maybe indicate this, then we know if there's many people or not many people. I think other than that, thank you very much for your questions, and I guess we'll be keeping in touch on Gitter. Is there anything else from you, Stuart?
No, I think that's good. So yes, thanks everyone for tuning in, and we'll hopefully hear from you again soon.
Okay, so Vitatus, I don't know, dropped out for whatever reason. I also, I'm sure he says bye as well. Okay, guys, I would say we'll talk more next week, maybe, and throughout the week on Gitter. Keep these applications coming, and especially also make sure that they're in Melange, because otherwise, like, it's nice that you send them to us, and that's great, so we can have a look and comment if there needs to be a comment. But if they're not in Melange by the day, then we cannot like, offer you a slot if we however many slots we get, but we cannot offer you a slot. Anyways, that's I think the bureaucratic thing that we need to do. Okay, bye everyone.
Okay, bye.